I'm your host, Nick Jikomes, and today I'm speaking with Dr. David Roberson. David is a neuroscientist and biomedicine entrepreneur. He received his PhD in neuroscience from Harvard University, and David and I actually did our PhD work at about the same time, which is where I was first exposed to his work, which focuses mainly on the neuroscience of pain perception and pain management. He is also the founder of Blue Therapeutics, a biotech company that works to develop better therapies for pain and other ailments, including opioid drugs that lack the addictive properties and overdose potential of traditional opioid drugs. Our conversation focused mainly on pain. How does our brain sense and perceive pain? Why does pain sometimes become chronic and last for a long time? How do various classes of pain drugs work to relieve pain? We discussed NSAIDs, non-steroidal anti-inflammatory drugs like ibuprofen. We also talked about opioids, including Oxycodone, Heroin, and Fentanyl, as well as some interesting novel pain drugs currently in development. A portion of the podcast has a visual component. We did a pretty good job, I think, of describing it for those just listening, but if you look at the YouTube version, David shows us some videos of the technology he has helped develop that allows for automated high-throughput measurements of animal behavior in ways that allow scientists to detect and measure pain in objective ways. Towards the end, we also discussed how this technology could be used in other ways, such as the characterization of novel psychoactive drugs and their effects, as well as applications relevant for psychedelics. As always, if you enjoy the content you're receiving on this podcast, please like, share, and subscribe. You can find the video version on YouTube, where you can like and subscribe to the video portion of the podcast. You can also find the audio version on Apple Podcasts or any other podcast medium that you might use. You can also sign up for a free weekly Mind and Matter newsletter at mindandmatter.substack.com. There you'll get access to upcoming guests and topics, other podcast news, links to other written content I've produced, as well as links to interesting research and other things that have crossed my path recently. Today's show is brought to you in part by Dosist, an all-natural cannabis company specializing in dose-controlled cannabis products made with plant-based ingredients. To learn more about Dosist, their products, and where they are available, please visit their website through the link in the episode description. This episode is supported in part by Athletic Greens. Their main product, AG1, is a comprehensive and convenient daily nutrition product containing 75 vitamins, minerals, and whole food-sourced ingredients with less than 1 gram of sugar per serving, no nasty chemicals or artificial anything. It's gluten and dairy-free and compatible with paleo, vegan, vegetarian, and ketogenic diets. AG1 is a quick and convenient way to supplement your diet to help ensure your body is getting the nutrients it needs. It comes in powder form, and you can mix it in water and drink it, or you can put it into a smoothie or a shake or something like that. I mix it into water and drink it with the first meal of each day, and it's super convenient. If you go to athleticgreens.com/mindandmatter, Athletic Greens will give you a free 1-year supply of vitamin D and 5 free travel packs with your first purchase. Their vitamin D product comes in tincture form, so you just take 1 drop each day. A large fraction of the population is actually vitamin D deficient, especially in winter months when we get less sun exposure, and vitamin D is super important for the proper function of the immune system and for a variety of other things. And there's even evidence indicating that vitamin D deficiency is correlated with more severe cases of COVID-19 in those who get infected. Every time I go into the doctor each year for a checkup, I'm always told that vitamin D deficiency is very common and I should be supplementing on a daily basis. So visit athleticgreens.com/mindandmatter or click the link in the episode description. You'll get a free 1-year supply of vitamin D with your first purchase. And with that, here's my conversation with David Roberson. David Roberson, thank you for joining me.
Thank you.
Can you start off by just telling everyone a little bit about who you are and what your background is?
Sure. My name is David Roberson. As you know, I am a neuroscientist and biotech entrepreneur. My general expertise and experience in over the past, say, decade has been in analgesic pain drug development. I also have a really strong interest in addiction, and there's a lot of overlap, as you might expect, between addiction and pain, especially in the drug development space, as well as trauma, which interacts with both the pain and addiction spaces quite a lot. So that's kind of, sort of my academic and professional interests. My training is I'm a PhD trained neuroscience. I also have an MBA. And you and I kind of crossed paths along both our journeys there. And yeah, that's kind of the 10,000 foot view.
Yeah. So you're, for people listening, David is a pain expert. That's one way of describing you. And I thought we would just start out with a very deceptively simple question, I think, which is, what is pain?
Yeah. So it's a good question, right? And it's one of these things that, academics have for decades really kicked around. And it's complex. It's hard to describe. Yet at the same time, we all get it. We all understand and know what it is. The official definition from the International Association for the Study of Pain is that pain is an unpleasant sensory and emotional experience associated with or resembling that associated with actual or potential tissue damage. So, it's complex, but at the same time, simple.
Okay. So like if you hear like a very loud sound or something, or someone suddenly touches you on the back to scare you, there's no real damage done to your body. There was no real threat there. The stimulus might in another context be perceived as painful, but the sensory side doesn't also come with that actual or potential tissue damage component. So we don't tend to call something like that pain, but something where there is physical damage that might have happened or that did happen, you would call that painful.
Right. Well, and even to your example there, a really loud noise, if persistent, will cause hearing damage, right? And so it does seem like the things that do cause us sort of pain and sort of trigger a reflexive withdrawal, whether it's to cover our ears or to pull away from a hot surface, those tend to be stimuli that are painful, or that are causing damage if they persist.
I see. And so how do we actually detect pain? So what does the sensory neuroscience of this look like? When you touch a hot stove or you get pricked with a pin, what's actually going on? How do our neurons actually distinguish those stimuli from something innocuous?
Right. So there are several categories of sensory receptors that are on, in the skin, for example. Among those are the TRP channels, such as TRPV1, the TRPM class of receptors, as well as other sensory channels that, together with TRP channels or other sensory modalities, can be perceived as pain. There are several different types of pain receptors, right? So the one that I think maybe most people might be familiar with, or at least have seen on their radar in the past year, is TRPV1. So TRPV1 is an interesting channel. David Julius discovered this channel a few years ago, and in 2021 got the Nobel Prize for his discovery, along with Artem Potapoutian, who discovered some piezo channels, which are responsible for tactile sensation. But the TRPV1 channels are both chemosensory, so they detect chemicals such as capsaicin that makes chili peppers spicy, and they also detect heat. So they're a non-selective cation channel. So it's they're in the membrane of the sensory nerves in our skin, and when they're activated, they open up and they allow ions in that causes depolarization, and that sends a signal to the brain that is typically perceived as pain.
Interesting. So there's different types of neurons in the skin, in the periphery, and there's a bunch of different types. Some of them, and they're all like tuned to different types of sensation based on these receptors or these channels that they have. And some of them focus mostly on mechanical, physical sensation. Some of them are more chemically oriented or temperature oriented. And broadly speaking, all of those things are the different lines that different pain signals can get into the brain from.
Exactly.
And so what about, people talk a lot about acute versus chronic pain, and I think we all intuitively understand those things, but can you unpack what the difference is there and how it connects to, pain that's detected in the periphery on our body versus pain that's in the head, so to speak?
Right. So that's a really good point. And, Generally speaking, chronic pain is a pain that is ongoing and usually lasts longer than about 6 months. There are varying definitions depending on different contexts and whatnot. But generally speaking, an acute pain is the pain that is caused by a stimulus. The stimulus can be present, such as when you touch your hand on a hot stove, or it can be a downstream sequela, such as inflammation caused by a painful stimulus that then continues activation or sensitization of those pain neurons. That is generally what we think of, or at least what I think of as acute pain. Chronic pain happens when those signals, let's turn it on its head. Chronic pain is when that perception of pain persists beyond the time that we would expect it to. For example, an injury may be healed, but you still have the pain, and it physiologically, structurally, there's nothing visible or detectable wrong, but you still are perceiving pain or pain-like phenomena, such as allodynia, which is something normally that didn't used to be painful but is now painful. So light touch that used to didn't bother you. If someone has, for example, a chronic neuropathic pain, that may be quite painful.
Interesting. So you mentioned a word that I think is really interesting: sensitization. So I want to unpack that a little bit. Maybe a really good real world example will be just right now. I have a big bruise on my leg from kickboxing, and if I lightly touch it, I get a little pain. Whereas if I do that anywhere else in my body, no big deal. How do we think about that? Is it literally that the area is inflamed, and so these pain sensors are being pushed against, and that's just making them more sensitive?
Right. No, there's a lot of things that go on that can cause this sensitization. And broadly speaking, the pain sensitization happens either due to peripheral mechanisms, so things happening at or near the site of injury, or central mechanism, which are things happening in the brain or spinal cord. So speaking about peripheral sensitization, which I think is the most easy to understand, in the case of your bruise, there are a lot of inflammatory mediators. Just crudely in the pain space, we refer to it as inflammatory soup, right? There's just a lot of different cellular released compounds and different components there of the inflammation process that cause pain neurons to be sensitized, meaning that it reduces the threshold necessary to generate an action potential and send that signal to your brain. So that's peripheral sensitization. The flip side of that, or I guess the other end of the line is that in the brain you have the perception of pain that occurs, and you can also have what's called central sensitization. And central sensitization occurs when circuitry within the brain itself or the spinal cord become sensitized. And by sensitized, I mean it takes a lower stimulus to generate a response than previously, right? And so that sensitization can be mechanisms that are within the brain, right?
Interesting. So I think you said it in an interesting way. It's very intuitive to think about peripheral pain. So if you've got a neuron, a literal pain sensor in your skin, and it becomes more sensitive, now if I push against the skin there, obviously I'm going to more easily feel something, including a painful stimulus. But what you're also saying is that inside the brain, there are circuits that become sensitized so that you do genuinely actually feel things as more painful, even though it is literally coming from inside your head.
Exactly.
Interesting.
And it's quite interesting, and it works in a way very similar to memories, right? So we can have a memory triggered of virtually anything, any experience we've had, and we just came through the holiday season. My family likes to put up a Christmas tree every year, and this year we went and we cut down a tree, like an actual green tree at a Christmas tree farm, and put it up. And immediately we put up this tree, and the whole house smells like Christmas. And it took me back to my childhood. I remembered that smell and and so, we have these memories that are stored, and pain can also, be stored as a memory. And, those memories can be recalled. Those circuits can be reactivated rather than from, a stimulus coming from the outside by central internal, brain processes. And that's not to say that it's imagined or artificial pain, or that it's, sort of a shadow of the real pain. It can actually be as intense and intolerable as the original pain itself. But when pain, when you have centrally triggered pain, or pain that arises from central sensitization, it is at least in part due to something going on in the brain.
Interesting. So we've got this distinction between peripheral and central pain that's arising from inside your brain versus being detected on the surface of your body. And then we've got this distinction between acute short-term pain versus chronic or persistent pain. Can you start to talk a little bit about what are some of the key brain areas or brain networks that one learns about if you want to learn about the central processing of pain?
Yeah, no, there are a lot of different circuits that influence, central pain processing. And I think broadly speaking, it's divided into the sensory component of pain and the emotional component of pain. And so the sensory areas are, as you would expect, the sensory cortex, right? And you've got, this sort of homunculus that represents different parts of the body. And so you do have a sort of almost like a geographic map on your brain of the different parts of your body. And those areas are activated to correspond with the area in your body where you're feeling the pain. That's the case, at least it's thought to be the case, regardless of whether the signal is coming from the periphery or, arising from central mechanisms, or it could be both, right? It could be that, you have a stimulus coming from your body that's sub-threshold normally, but because you have sensitization, it's now perceived as pain. But you also have emotional. So, the emotional perception of pain involves, all the different components of the amygdala that are involved with, fear and aversive emotional sensations. And then you also have even deeper sort of, periaqueductal gray and brainstem areas that are involved in pain. And I like to think of pain as a very primitive sensation, right? And it's from an evolutionary standpoint, one of the most essential sensory feedback mechanisms that an organism can have is to detect danger, right? Mm-hmm. And so detect something that could cause injury or threat to your life is something that's pretty hardwired and involves some really primitive brain areas.
Yeah, that makes a lot of sense. What in terms of the evolutionary and ethological function of pain, one way to think about this is to ask the question of what happens when an animal, a human or a non-human animal, cannot detect pain. What does that look like, and what tends to happen to those creatures?
Sure. No, that's a really interesting question. And there have been several different genetically induced or genetic problems that people have where they can have inherited lack of sensitivity to pain. Some of these have been pretty widely studied, and typically what you see in these folks is that they have repeated injuries. They can develop, interestingly, they can develop normal, relational and cognitive functions, and they, don't necessarily have delayed, cognitive development, but they will have repeated injuries. They often have repeated infections. As children, they will be frequently injured and have, broken bones. And in things, and they tend to take more risks, right? And it used to be that you would see these people would be sort of discovered by the scientific community because they would be, working in a sort of almost in an entertainment type role or job, putting needles or knives into their body to show people that they could, tolerate pain and almost like a busker, but doing these feats of superhuman pain tolerance. But so these folks do have, when you don't have the ability to feel pain, it is problematic, right? And these folks tend to have a shortened lifespan and end up with a lot of medical problems.
Yeah, I had one conversation on the podcast with a scientist named Matt Hill, who focuses a lot on the endocannabinoid system. And he told the story of a woman from the UK, I believe, and somehow she was discovered. She has a very rare genetic mutation involving her endocannabinoid system. The end result of that mutation is that she had very high levels of this endocannabinoid called anandamide. Mm-hmm. And there were two sort of interesting phenotypes there, in my view. And I'm hoping you can connect something here for us, because it sort of shows, I think, the link between physical pain as we normally think about it and what you might just call emotional pain. Mm-hmm. And she was both, she was very immune to pain, basically, of all kinds. So she had a very high pain threshold. She was the type of person who could, burn her hand on the stove easily and not even notice it. But she was also very happy. She basically was immune to anxiety. And so she was just in this persistent good mood. And so I'm wondering if you could start to talk about the link there between what we would think of as perhaps being separate things, the physical sensation of physical pain and anxiety and things like that.
No, that's a great point and interesting topic for me personally. I think most of us, we think of physical pain and emotional pain being two different things, right? It's but as I said, physical pain does have a very strong emotional component to it, and there is sort of some philosophy around this as well that a lot of the mindfulness practitioners differentiate between pain and suffering, right? Which suffering in their definition, incorporates both a perception of this aversive stimulation or stimulus, but also an intolerance of it, an emotional intolerance of it, right? And so, it's interesting, and I think it does tie into, and I hope we'll get to this in our conversation. It ties into how addiction and sort of seeking after an escape, it can be pharmacological or any other type of escape from pain, is often sort of the flip side of the coin of someone who have people who have chronic pain states, right? They often have trouble with addiction, and it's not surprising, because if you have persistent pain, either due to central sensitization or due to ongoing injury, it's no wonder that people want to try to diminish that pain in some way, right? And so the ways, and it goes both ways, right? So people who have physical pain and become addicted to, for example, opioid drugs, often also have psychological or emotional struggles or pain, right? And emotional pain that the opioids also help with, right? And so that's one of the things that I think I didn't realize until I really got into this space, was that opioids, while they're really fantastic analgesics, they work really well to reduce the perception of pain. They also reduce the emotional processing of pain, and therefore, when someone carries a lot of trauma or psychological trauma that is really difficult to manage and sit with, the opioid drugs have a way of dampening that, right? And so It's thought that that's why the vast majority of people who are prescribed an opioid or try even recreational an opioid will never become addicted, no matter how often or they're exposed to it. We see this in animal models as well. But there are certain people that will, right? And one hypothesis is that these people also have ongoing emotional pain that they're trying to process and deal with, and that the opioids help with that, right?
Yeah, interesting. I want to circle back to that when we talk about opioids in more detail. One of the things I want to clear up front to help people get a good foundation here is how we actually measure pain. And so let's start with humans, because many of us will have actually done this, and I'm still sort of blown away. The maybe 2 or 3 times I've had to do this at the doctor's office, where I say I'm in pain of some kind, and they say, well, how bad is it, scale of 1 to 10? And I remember being asked this the first time, and I was like, how do I even answer that? Don't you have some other way of assessing this? And they basically told me, no, you have to tell us on a scale of 1 to 10, and then they have some kind of rubric. So, with something this subjective, why is it that it's so hard to measure pain other than asking someone?
No, it gets to exactly the what you said, and it is subjective, right? And the exact same stimulus, if you take a thermal stimulus and apply it to the forearm of someone and apply a certain heat and energy through that, some people will find it more tolerable than others, and certain people will find it quite painful. And so it is very subjective. And in humans, pain is primarily detected by asking people, how does this on a scale of 1 to 10, with 10 being the most severe pain that you've experienced or could imagine, right? Mm-hmm. And so I remember the first time I personally realized the impact of that question. And I was on a flight back from transatlantic flight, and my parents had actually been in a plane crash back here in the U.S. And I was coming back with my pregnant wife, and trying to coming back to check on my folks, and fortunately they survived and ended up recovering. But at the time I didn't know that, and I had developed a kidney stone like 4 hours into a 13-hour flight. And there was a urologist on board. I didn't know what it was. I hadn't had a kidney stone before, but there was a urologist on board who asked me, he's like, how severe is this pain? And I was like, this is like a 9 or a 10. I've never, ever, I didn't know I could hurt this bad. Right. And so, however, had you asked me, the day before, if I had, broken my finger or something that would be quite painful, but not kidney stone painful, right? I would have maybe called that an 8, a 9 or a 10, right? Mm-hmm. And so it's so subjective. And I do feel like, my wife has given birth to all of our children. Obviously, I didn't do it, but and I think a lot of women have this experience where they experience childbirth and realize that, God, this is like the worst pain imaginable, right? And so it's very subjective and it's very relative, but that's really the best we've got.
Mm-hmm. Is there any reason to think that the brain itself is sort of relativizing pain measures, meaning like, if you go through something new, like a kidney stone or a childbirth that's excruciating, that your brain sort of recalibrates all of the other things you've experienced before, such that subsequent episodes of those things are perceived as less painful?
I don't know. It's a little outside my little niche of pain, but that seems reasonable. Right. Certainly that's my experience. Right. When, but at the same time, right. So my relative pain perception changes when I've experienced something more painful than anything previous, but it doesn't make, what used to be my 9, what is now a 7, any less painful. Right. It just means that there's a whole nother level, right, of pain that I'm capable of perceiving. So, yeah.
Yeah. And then, if we measure pain in humans by asking them how painful it is, simply because it is so inherently subjective, this brings up another question, which I think is fascinating, which is, we develop so many of our drugs and our tools for treating things like pain and other things in animal models.
Yes.
We do this for pain, but obviously you can't ask a monkey or a mouse or something, right, how much pain are you in? So how do we actually assess pain in animal models in the context of drug development?
That's a really great question. So, the standard ways that this is done is that, and these methods have been around for 50, 60 plus years. But, the model organisms that we typically use for many areas of drug development, in particular for development of neurological drugs, right? So including analgesics, which are pain drugs, are to try to model the disease that we're trying to treat in rodents. So the way we model or test pain in rats and mice is to apply a stimulus that is, hot. For example, like a heat stimulus is one example. So a thermal stimulus that's hot enough that it's perceived as painful by humans, presumably perceived as painful by an animal, but not so hot that it's just immediately causes severe pain, right? And so you apply a stimulus such as a heat stimulus to the paw of a rodent, and you wait and you see how long does it take before they perceive the stimulus and pull away voluntarily, right? So in rats and mice, you can apply a roughly 50 degrees Celsius stimulus, which is about like the outside of a coffee cup, right, with hot coffee in it. And so you apply the that stimulus, and if you ever touch a hot, warm coffee cup, you can hold it for a few seconds, and it's warm and it's not painful. And then it gets painful pretty quickly, and it can get so painful that you got to set it down, right? And this is what we see in rodents, right? So you apply a heat stimulus, typically with an infrared beam of light, to the underside of a paw of an animal that's in a cage that has a wire floor. And you sit there literally with a stopwatch in hand, and you say, how long does it take for this animal to pull their paw away? And typically, somewhere between 5 and 15 seconds. And then you give them a pain drug, and you see if that moves the needle in the direction toward extending the time that they can tolerate the pain before they pull away. And the flip side of that is if you have, arthritis or any other sort of disease that can be modeled in rodents, that tends to make them more sensitive to this thermal stimulus. So that's generally how pain is modeled in rodents, and these are called reflexive withdrawal assays. We can do the same thing with a mechanical stimulus. So we can poke the animal with a certain force on the bottom of the paw and see how much force does it take before they pull their paw away from a sort of monofilament, almost like a little piece of fishing wire. Right? You just poke them, and eventually they'll pull away. And this is the best we've got generally. I mean, there are some other ways. There are place preference assays and some more complicated things that are quite time. They're takes a lot of animals and takes a lot of time to do those assays. And frankly, they're not that much better, if any, than these reflexive withdrawal assays. And so, but there are a number of problems. Chiefly, I think, in my opinion, the biggest problem is that we are not necessarily even detecting perception of pain in rodents with this, right? So it's possible and in many cases probable that when you apply a heat stimulus to the bottom of the paw of a rodent, that it's pulling its paw away as a reflex, right? And that reflex, just like when the doctor taps your knee and your foot jerks, that reflex is not due to a perception or a voluntary withdrawal, right? It's more of a reflex, right? It happens independent of our perception and intention. And so that's important because when we take pain drugs, when humans take pain drugs, the intent of those pain drugs is to reduce the perception of pain, right? And so for that reason, and likely others as well, but pain drugs and pain drug development has been an extremely difficult venture. And unlike most drugs, well, actually, I won't say unlike most drugs do not. Let me just back up and say this a different way. So, when you take a drug and you develop it in animals, and then you go into human trials, in many fields, you might have 70, 80% of the response rate in humans that you have. I'm sorry. I'm totally like talking circles around myself here. All right. Let me just start with pain. When you develop a pain drug and test it in rodents, and then you go into humans with that pain drug, 9 times out of 10, it fails either due to lack of efficacy in humans or side effects that were not predictable, right? But in pain drugs, that lack of efficacy, lack of effective predictive potential of the efficacy of the drug is particularly problematic.
I see. So many drugs that seem like they're going to be good for pain in a rodent model just don't end up being good for humans.
Exactly. No, exactly. And it's a real problem. And the other piece of this is that these assays are extremely difficult to do. There's a lot of variability. When you have a scientist like myself sitting there, applying a stimulus to an animal, waiting for it to pull its paw away, and you're timing it with a stopwatch. There's a lot of variability in what I might call a 6-second delay before this animal removed its paw. Might be 8 seconds or 4 seconds for someone else, or they might not even call it nociceptive withdrawal, right? They may, which is the term that we use for something that's pain-related withdrawal, right? Sometimes, the animal might just start walking away, right? Mm-hmm. Is it painful or not? And so what there's a lot of nuance around, well, it's a nociceptive or pain-related withdrawal if the animal pulls its paw away and flicks it, but not if it just lifts its paw and starts walking. But as you might imagine, that's very subjective.
Right.
So, because of that, it's important that when you do pain studies, both in an academic setting or in a drug development industry setting, that the same investigator measure all the animals that are in a particular study, right? So you want the same person making all the measurements across all the time points in all the different groups, which is a real bottleneck, and it makes pain drug development very costly, and it's a really inefficient way to do things, and not least of which it's a really it's not very fun to do these studies, right? I spent I don't know how many hours doing these types of studies at night, because pain, rodents are also nocturnal, right? So they're more active in the night, in the dark cycle, and so I tried to come up with so many different ways to improve on this, using night vision goggles and doing it in the dark to see if it would get more consistent results, and maybe the animals would be less likely to fall asleep if it was dark. But yeah, it's very problematic. So
are there any new tools in development that take advantage of any, emerging technologies to address this type of problem?
Absolutely. And this was actually half of my PhD project. So did my PhD with Clifford Wolf at Harvard Medical School and Boston Children's Hospital. And half of my PhD project was developing new approaches, right, to try to come up with better ways. And I tried a lot of different things, videotaping mice from different angles, and different ways to train animals for place preference. But ultimately, the thing that sort of really stuck and has worked the best, and actually has been something I've spent a good part of my career on, is developing ways to use total internal reflection within a glass sheet, which is to basically use this phenomenon to create a light signal that gives you a readout of how much pressure an animal is putting or rodent is putting on the floor beneath their feet. And with this light signal and, for example, different types of machine vision, machine learning algorithms, you can come up with a really a much more sensitive and objective way to measure pain in rodents.
Interesting. So literally you can use you can use tech to tell quantitatively how much pressure an animal is putting on its paw. So if you imagine like an animal that's walking with a limp, they're going to change the pressure and you'll be able to measure that directly.
Right. And, another really important piece that I'd like to put in at this point is that, rodents are actually prey animals, right? So they're intrinsically fearful of predators. And we are, in the case of laboratory mice, we are their predator. Right. And there is a phenomenon called fear-evoked analgesia. So what happens is that when investigator is present, you see reduced pain the outputs are reduced, the thresholds are increased, right? So it takes a higher stimulus to get the withdrawal. And where you really start to see nuance around this is that it's rodents show higher pain levels when female investigators are doing the assay than when male investigators are doing this. And Jeff Mogul at McGill did some really interesting work on this 10 or 15 years ago, where he showed that if you do these standard reflexive withdrawal assays in mice and rats, and you have a female investigator doing the work, you get this one threshold level. If you have a male investigator, the animals appear to have less pain, right? So their pain threshold is higher, and they seem to be experiencing less pain, or at least their withdrawal threshold is reflective of that. But you can get you can get the same response as you get with a male investigator simply by putting the t-shirt that a man has worn overnight and his pheromones have gotten onto the shirt. You put that in the room with the animal, suddenly it has the same response as if there was a man in the room.
Wow.
Right?
So the basic idea here is, if men are generally bigger and that much scarier than female humans, to the mouse, what you're saying is basically that the mice are probably more scared of the male investigators. Yeah. Therefore, their adrenaline might literally be jacked up higher. And so they can tolerate more pain.
Yep, exactly. Right. And so, there's just so many problems with having a person present doing these assays. And so this technology that Clifford and I came up with, I also should mention, co-inventors on this are Bob Data and Alex Wilchko, who were quite helpful, when we were trying to ideate and really think about how to go about this. But ultimately, we came up with a way to put a mouse in a box. The glass floor of that box has sensors within it, right? That it's got that allow, as the mouse walks around, each of their footprints creates a light signal that's seen from below, and you can very clearly see if the animal has a limp, right? And whereas normally, if you take one of these videos, and I'll show you, I've actually got some examples I can show you, but if you take a mouse in a box that's say injured, right? Say it has arthritis. It's really hard to detect from watching the mouse walk. It's really hard to see if it has a limp or if it's actually favoring one hind paw over the other. You just can't see it from above, right? And the hypothesis there is that mice, being prey animals, have evolved to hide signs of injury from the viewpoint of the predator. Right.
Yeah. The predator's naturally going to want to pick off the one with the limp. Yeah. Exactly.
So it really makes a lot of sense. And frankly, even if natural selection won't do that, the types of selection that we do in the lab absolutely will, right? Because any animal, we've bred mice in the lab for 50, 100 years. The strains that we have been selected over time. If an animal shows any sign of injury, we don't breed it. right? So we're actively selecting for animals that do not show signs of injury or disease. Because when we take a mouse out of the breeding pool, it doesn't mean that we've removed all the mice with a limp, right? Say we're taking out a mouse that has a limp, right, or is injured. We're only taking out the ones that show a limp, right? So even we have actively done what nature has been doing for millions of years. So all that to say, the idea was if you put a mouse in a box and leave the room and look at it from below, a viewpoint that predator has never seen, we should see some interesting things, and that's absolutely what we find.
Interesting. Yeah. Can we actually see some of that?
Sure. Just a moment. Let me pull this up.
So for those just listening, we're going to look at some video data now, and we'll describe it verbally so people can follow on the audio only version, but you will be able to actually see this on the YouTube version.
Sure. So this, what I'm showing first is just some snapshots, some still images of different types of mouse behavior viewed from above versus from below. And the point of this is just to show that even if you're talking about anthropomorphically defined behavior such as paw biting or licking or scratching, right, grooming, that if you look from above, it's really hard to tell and differentiate between these behaviors. So if you look here over the left-hand column, paw biting versus licking, paw licking, or you can see that, like, looking from above, they look like they're doing basically the same thing. Mm-hmm. But when you look from below, you can see so much more detail, right? You can see exactly where the animal's mouth is and where their paws are. And so, this was the first hint that I got that, okay, I'm on to something, right? So I'd made some devices to look from above and from the sides of the animals. And it wasn't until I put a camera underneath, I was like, okay, now this is the viewpoint that we want. So the next thing we did was to see if I can get this to move forward. So this, I'm now showing a schematic for those of you listening. It's a side view of what this technology looks like, right? So on the top, you have a mouse that's inside of a box. The floor of the box is made of glass, and beneath that glass, you have a camera. In this case, we're using near infrared light to illuminate the animal and to illuminate the paws. Near infrared light is invisible to mammals, so humans and mice cannot see near infrared light. So it gives them the perception, the illusion that they're in the dark. Right. So the animals apparently in the dark, and they're nocturnal, so they feel safe. Mm-hmm. There's no humans in the room, so they also feel more safe. And we have two different light sources. The first light source is over here on the left, where it says near infrared trans illumination. And this is simply an LED light shining from below the animal through the glass to illuminate their body from below. And then we have a separate set of lights that are shining into the long edge of the glass. So these lights are totally internally reflected. It's a phenomenon called frustrated total internal reflection. And every time a beam of light hits that glass air interface, it creates an evanescent wave. And that evanescent light wave diminishes exponentially as it moves further from the glass. And what that does is it creates a pressure sensitive signal. So as the animal presses their paw down on the glass, the sort of ridges in their skin come more and more in contact with the glass, and you see that that signal between the paw and the glass becomes brighter the more pressure is pushed down. And in this case, because that signal is, on the one hand, you want to see the whole body, which is why we have this transillumination signal. But that transillumination signal can interfere with detection of exactly the precise time when the paw hits the glass. So I'm not sure how clear this will be to your listeners that are not watching the YouTube video, but if you imagine you're have a flashlight looking through a piece of glass, and on top of that glass, a mouse is walking around. Well, if every time the mouse puts its paw down, the paw creates a little light signal, and you're also shining light from below, those two signals are going to kind of cancel each other out, and you're going to be able, and you're not going to have as clear a distinction as you would if you didn't have the flashlight on. Mm-hmm. And so there are a couple of ways that we've used to mitigate this issue and correct for it. And one is to use simply two different wavelengths of near-infrared light, mm-hmm. with and use two cameras, right, with a bandpass filter on each one, so that the wavelength of light you're illuminating the animal is different than the wavelength of light that you're illuminating the paws. And the other way we've done this is to alternate the illuminations on different video frames. So one video frame, you look at the paws, and the next video frame, you look at the body. And both work equally well. But
I guess the punchline here is, you've removed humans from the environment. You're doing this in the dark in a situation where the animal's sort of maximally comfortable and able to go about its business unfearfully. And two, you've used cameras and infrared light in a clever way, such that every time that a mouse steps on its paw, you can literally see how much pressure that's being put on it.
Yeah, exactly. And I've got some videos here that really are videos worth 1,000 words. So on the left is the paw image, on the right is the mouse. And then I'm bringing them together here and kind of overlaying them so that you can see what that looks like. And this is just showing a mouse sort of just, he's scratching, kind of walking around a little bit. But with the signal from the paws, we've color coded it so that it's like a heat map. Mm-hmm. And that way you can sort of intuitively see what the mouse is, how much pressure is both within each paw and what the difference in the pressure is between the two paws.
Yeah, no, I mean, it makes perfect sense. Like I'm looking at this mouse, I can tell just by looking at it from below that it's standing back on its hind paws and not on its front paws. But then the heat map makes it clear what the computer is going to see, which is the pressure is on those hind paws and it's not on those front paws so much.
Right, exactly. And so I've got a couple more videos here. This next video is showing sort of the workflow. So, it's not enough to simply, show the mouse walking around and detecting limp, which I'll show you in a moment. We really wanted to be able to automate this and let machine learning algorithms tell us, what's going on. And so in the workflow there is that we basically, used these machine learning or machine vision algorithms rather to identify the four paws and the tail and the snout of the animal, and then on each video frame to orient the animal so that it's always facing the same direction. And this makes it much easier for subsequent analysis of each video frame, because you always know that the left paws are going to be on the left side of the image and the right paws are going to be on the right. And it's not going to change when the animal turns around and goes the other direction. And then the next video here is showing, the unaligned frames. And this is where we've used the algorithm to look at each of the paws, and the yellow here is identifying the left hind paw of the animal, and the blue is identifying the right hind paw of the animal. And we can also use the same algorithms to identify each of the other paws. And I want to point out here, we're using a lot of some off-the-shelf machine learning algorithms. Deep Lab Cut is a toolkit that we find really helpful to work on this. And we actually have a paper that's under review right now, so I don't want to preempt where it's going to be published, but we do expect to publish this in the next couple of months, and all of these algorithms and the source code there will be made publicly available. So
interesting. Yeah. So now you've got a way to it's really an objective way to measure pain in a more naturalistic setting.
Yes. And, what we find is that we can, in doing this, not only do we see that it's really clear when an animal is in pain versus when they're not in pain, in particular if the pain is in one of the hind limbs, but we also see that we can reverse that pain with a pain drug at a much lower dose than necessary to reverse reflexive withdrawal. And so it's a much more sensitive assay, and it's backward. It backwards translates. All existing analgesics work really well, and it's our hope that it will also be quite predictive of future analgesics, and that we'll be better able to predict. And the last thing I'll mention that I think is I'm really excited about is that whereas typically we have to use somewhere between 10 and 12 animals typically per group to get statistical significance in a pain assay, with this approach and the machine learning analysis of these data, we can do the same thing with 3 or 4 animals. And so we're cutting, the number of animals needed to be used pretty dramatically. And additionally, we can actually do high throughput screening of behavioral phenotypes of pain and analgesia in mice very efficiently.
Mm-hmm. I would love to start talking about some of the different kinds of pain drugs that are out there and how they're actually interfacing with the nervous system. So if we go off of the screen share, I think a good place to start, perhaps. Oh no, do you have a video that's good for this?
Well, yeah, actually, let me show one last video here of the pain.
Okay, yeah.
This goes with what I was just saying. So this is a mouse pain model on the left, and you can see that his left hind paw is not as bright as the right. It's the one he's scratching there with, and then when he the same mouse, after we give him an analgesic, and you see that those hind paws are now equal, right? So on the left, he's really favoring one paw over the other, and on the right, he's no longer doing that. I'll stop the share here, and then we can move on.
Yeah, that makes perfect sense. So the animal's got a paw problem, favoring one paw over the other, and then you give the pain med, and basically that goes away. He doesn't notice.
Right. No, exactly.
Interesting. So there's a bunch of different types of pain drugs.
Sure.
This is, unlike other areas, this is, a place where most people listening will have direct experience with at least some of these, and we've all heard of probably most of them.
Right.
But I wanted to start with maybe just sort of an everyday type of pain drug that you can go to the store and buy, and that's NSAIDs, non-steroidal anti-inflammatory drugs. So can you give us, starting with the very basics, what are the NSAIDs that people have heard of? And then can you get into like what they actually do to alleviate pain? Right.
So, NSAIDs, as you said, they're non-steroidal, they're anti-inflammatory drugs, and they relieve pain by reducing inflammation. And, they work quite well for a lot of different types of pain, musculoskeletal pain and strains, and, post-operative pain, even certain types of headaches, arthritis, colds and flu, pain related to that, generally respond quite well to NSAIDs. Here in the United States, ibuprofen is quite widely used. In Europe, the diclofenac is really commonly used over-the-counter NSAID, and they work actually quite well for acute inflammatory pain.
Interesting. And then, do you know what the mechanism is there? Or is it like a brain receptor they bind to, or is it something else?
Yeah, there are 2 different types of NSAIDs. Some of them are non-selective, but others are COX-2 selective. And, the COX-2 is an enzyme involved with inhibiting pain, but also involved with thrombosis and other things. And so, largely you're interrupting or intervening in the function of an enzyme.
Oh, I see. So there's an enzyme in the body that's naturally involved in producing stuff related to the inflammatory response, and the NSAIDs get in the way of that.
Right.
Interesting. So how does that differ from, so we've all probably taken these types of drugs at some point, ibuprofen or whatever. How does that differ from something that's more potent, like an opioid?
Sure. So opioids, work on a different system, right? Opioids work on opioid receptors, which are present throughout the body, and they're present in the peripheral nerves, as well as in the spinal cord and in the brain. And opioid receptors are the activity of opioids as analgesics is probably best demonstrated in the spinal cord, where you have inhibitory circuits, and when you activate opioid receptors, it actually inhibits that pain signal from being sent up into the brain. And so they work really well for blocking pain, because they actually can block those pain signals and block the transmission of the pain signals in the spinal cord. And they also work in the brain in some of the same circuitry that's involved in processing of pain, both in the somatosensory perceptive areas, as well as the emotional areas of perception in the brain.
Mm-hmm. And is that tied to why they're not only diminishing the perception of physical pain, but there's also a euphoria that's tied to taking an opioid?
Yeah, I mean, it's I don't know. I think that those things are separable, but there are certainly a lot of overlapping circuits, and the mu opioid receptor, which is the one that's predominantly activated by conventional opioid drugs, is responsible both for the pain relief and for activating the circuitry, the reward circuitry of the brain. Yeah.
I see. So activating that receptor has analgesic effects, pain effects, and it also has this sort of emotional, feel-good pleasure effect.
Yes, exactly.
And so what, I suppose that's tied to the addictive properties of these drugs.
Yes, certainly. Right. Opioids are addictive for a number of reasons, right? They're, one certainly is that they do activate these reward centers. They cause euphoria, right? But another thing that makes them quite difficult to, makes them quite challenging as a therapeutic, right? And contributes to really the opioid crisis is that two factors. So one is that you pretty quickly, when you start taking an opioid, develop a tolerance, right? So, the first dose of opioid that you take for, if you've got pain, may produce, 80 or 100% even of pain relief, analgesia. But if you continue to take that drug, within a day or two, you'll start having to take more and more of the opioid to get the same pain relief. Right. So there's this escalating dose that happens simply to maintain the same level of pain relief. You have to keep taking more and more and more. The other thing that happens is that when you stop taking an opioid, if you've taken it for a matter of days or weeks and you stop taking it, then you'll have withdrawal symptoms. So not only do you have to take more and more to maintain the same level of pain relief, but when you stop taking it, you just feel you have like a flu-like symptoms, and you just feel terrible. And your pain is even worse than if you hadn't started taking the drug to begin with. So it's really problematic, and opioids for that reason are the best practice is really to only use them for acute pain. Although there are patients who do take them for chronic pain and sort of seem to have a ceiling effect to that tolerance, but it's these factors of being both euphoric when taken at high levels, and requiring increased doses, and then causing withdrawal when you stop taking it, are the reasons that we have the opioid crisis.
What about what about the differences between different types of opioids? So, for example, Oxycodone is a famous prescription opioid, I believe. But then, what about something like that versus, say, heroin? Like, what's are they more or less the same drug, or are they quite distinct?
Well, they're more or less the same drug, right? So heroin and morphine are actually effectively the same, right? So and the way they act on the mu opioid receptors are exactly the same, right? So it's the opioids, whether you're talking about a drug of abuse, heroin, or you're talking about a purely prescription drug such as oxycodone, which certainly can be abused, their mechanism is still by acting on this mu opioid receptor. And they activate that mu receptor. It's present throughout the body. It's present in the reward circuitry of the brain, as well as in these pain relieving circuits in the spinal cord and elsewhere. Right?
I see. So for opioids, broadly speaking, in terms of the mechanism, the first thing people should think about is mu opioid receptor.
Yep. That's the one that, there are three canonical opioid receptors, but the mu opioid receptor is the one that is activated by all of the opioid analgesics on the market.
What about this is another one that basically everyone has heard about at this point, but in my lifetime, I went from having no idea what this was to this thing coming to the forefront of everyone's mind and US culture right now, which is fentanyl, which is I believe one of the, if not the most potent opioid drug that's out there. So why was this developed? What makes it so potent, and why is it doing what it's doing right now?
So fentanyl is an extremely potent mu opioid agonist, right? So it activates the mu opioid receptor at extremely low concentrations, right? So the reason it's so potent is that it requires such a small amount of it to activate the mu opioid receptor. It just hardly takes any. It was developed as a prescription intravenous use analgesic for surgery, and it's still used in that context, and it works quite well. I think the reason that it's in the vernacular of all of us now, and everyone's heard of fentanyl, is that because it requires such small quantities, and because opioid addiction is such a problem, particularly in North America, the illicit drug providers and the folks in the labs around the world that are making illicit opioids have found that it's much easier to make a little tiny bit of fentanyl and ship it wherever it needs to go around the world to the end user, and then dilute it in something that's not fentanyl and sell it as heroin, right? So whereas a certain quantity of heroin might be fit in a thimble, the same potency quantity of fentanyl might fit on the head of a pin, right?
Wow. So there's an economic drive there. It actually reminds me of the illicit cannabis market, where the economics were such that people wanted to get as much potency into as much matter as possible because it made it easier to transport this without getting caught.
Right. And it's really problematic. And personally, I think that we've made it worse with the war on drugs and the way we've criminalized people who suffer from addiction, and rather than treating it like a disease and a medical problem that could be solved with medical tools, and we've treated as a criminal act, which it just exacerbates the problem.
Why is it so deadly? Is it because it's potent at the mu opioid receptor?
Well, so the reason all opioids can be deadly is that they act in this pre-Boettinger complex in the brainstem, where they inhibit, they cause respiratory depression, so they slow our breathing. Right? So typically what happens, and this is the problem with fentanyl, is someone who is addicted to opioids, oftentimes, they may have gotten it prescribed by their doctor for legitimate pain, and, begin taking more and more of it also as prescribed, but then find it really difficult to get off, or find that the reward that they get from it, whether it's the euphoria or simply the relief from some emotional or psychological pain that they're experiencing, is enough that they then get addicted to it, right? And as they continue to take it, it works less, and the efficacy diminishes, and they build a tolerance to it. However, you don't tolerize to the respiratory depression, right? So we even see in the clinic, right? So there are patients that even under the supervision of a physician, you'll start to see respiratory depression as they give them higher and higher doses. So it's not necessarily something that is someone just decided they wanted to get really, really high and take a ton of it, and they overdose. No, I think most often what happens is that people know exactly how much opioid they need to get their fix, whether they're looking for a high or they're simply trying to keep the pain at bay. They know how much they need. They think they're getting a certain formulation. They think they're getting heroin, or they think they're getting morphine or oxycodone, but instead they're getting something that's laced with fentanyl, and it may not be mixed in well, so that one dose of this powder has a lot more fentanyl in it than another dose of this same mixture. And eventually, if you keep elevating the dose, you get to a point where it makes you unconscious, and then you stop breathing. And
I see.
Die, right?
So eventually, if you take enough of an opioid, and it doesn't actually matter which opioid, it just turns out that fentanyl is the most potent, so you don't need that much. Yeah. It just slows down your breathing, and at some point, it stops your breathing.
Yes, that's right.
And you basically just go to sleep, I guess.
Yeah. No, it's tragic and really sad at so many levels, but and it's it's a big problem. With COVID, obviously, we're not hearing about it nearly as much as we did, a few years ago. But actually, during COVID, the number of deaths has really soared. And just this year I should say it's 2022 now, but in 2021, we just passed 100,000 deaths per year due to opioid overdoses in the U.S.
I think that's actually more than COVID, or am I wrong about that?
So the cumulative COVID deaths in the U.S., I think, are now up in the hundreds of thousands, right? Mm-hmm. But I can say that the opioid deaths, there are more deaths per year in the U.S. from opioid overdose than cardiovascular disease, cancer combined.
So it's near to the top of the number one cause of mortality.
Yes.
Wow.
Yeah.
Another area that I want to ask you about is cannabinoids, because I know there's some overlap here. A lot of people talk about cannabis for chronic pain, and I know there's some interesting synergistic effects that can apparently happen between opioids and cannabinoids, such that perhaps you could take something with THC in it, say, and that would allow you to get the same level of pain relief using a lower dose of your opioid. Do you know anything about what's going on there?
Yeah, I actually don't. I should probably. As you know, in science, a lot of times you get sort of siloed into your little narrow niche, and I know a bit about it, but I don't feel enough to really give too much detail. Other than there certainly is an additive effect, right? Mm-hmm. And there's a real synergy between not only cannabinoids, but a lot of the different analgesics. And the cannabinoids, I like to think of as sort of they change the synaptic signaling between neurons, right? And so they kind of act as a way of fine-tuning a lot of different processes, including pain, right? So it's really not terribly surprising that when you take a cannabinoid in addition to any of the other analgesics, that people find it beneficial.
Mm-hmm. What about I imagine that there's a lot of effort to develop novel pain drugs, and I know that you've been involved in this in different ways. Yeah, so, high level, how does this work generally speaking? And is it possible, to make a novel pain drug that's, say, derived from an opioid, such that it preserves the pain management component, but gets rid of things like the addictive potential or the respiratory depression aspect?
Yeah, no, there's a lot of folks doing interesting work in this space. Myself and a couple guys at Harvard that I was in the lab with started a company, Blue Therapeutics, 5 or 6 years ago, doing this work, and that company is still ongoing and doing some interesting work. One of the ways, before I get into to Blue, typically the way that people have gone about trying to develop non-addictive or less addictive opioids is different ways of formulating them, right? So you can imagine that if you make an extended release formulation, right, or something that within the extended release case, you might be able to just take one pill and you have sort of a slower, steady state, and so you don't get the peak in the serum levels that could sort of trigger that euphoria. In theory that works, but in practice, people can just take, if they want to get high from an extended release opioid, they can just take a couple of them and then they're high for a long time, right? And so that's actually what happened with Purdue Pharmaceuticals and the Oxycontin, right, which is an extended release oxycodone. So that was the first attempt. A lot of the first attempts were extended release formulations, which really ended up causing more problems than they helped, I think, in a lot of cases. Other ways, other folks have used biased agonism. So, the opioid receptors are G-coupled protein receptors, GPCRs, and you can when you activate a GPCR, there are downstream signaling cascades that are respond to their activation, and you can design molecules that favor one downstream signaling cascade over another, and see some differences in the clinical profile of those. And there are some companies doing that. Other groups have tried to come up with peripherally restricted opioids. Mm-hmm. So these are drugs that don't enter the brain or the spinal cord, but act only in the periphery, act only in the body, right? On the opioid receptors in the skin and the muscles and whatnot. And those have also shown some limited promise, but in clinical trials haven't worked that well. In my opinion, it's not terribly surprising because chronic pain, which is what is sort of the big bad wolf of the pain space, that's the most difficult to treat and where there's the greatest need. Chronic pain is largely due to central sensitization, and so if the central sensitization is driving the chronic pain and your pain drug is peripherally restricted, it's probably not going to work all that well for chronic pain, right? And so it's going to have a limited use case. But one approach that I think is just the most interesting to me, and like I said, I gave several years of my life to this, is using receptor interactions as a way to target subsets of opioid receptors. So this could be done using to target any receptors in the brain or really anywhere in the body. But in the pain in the opioid space, a guy named Phil Portuguese, who's a medicinal chemist at University of Minnesota, together with Ajay Yakarala, who is a PhD neuroscientist who did his PhD with Phil, they came up with some molecules that activate opioid receptors only when they're interacting with each other, right? And so, for example, I mentioned earlier, there are 3 different types of opioid receptors: mu, kappa, and delta. They are present in different parts of the brain. Some areas they are present together. Other areas, only one or the other will be present. And so Ajay and Phil came up with a way to design molecules that activate these receptors only when they interact. So the one that Blue Therapeutics pursued and still is developing toward the clinic is a drug that acts on mu kappa interactions. So if you have a mu opioid receptor, which is present in the areas for the reward circuitry, the pain relief circuitry, as well as some of these areas that underlie tolerance and withdrawal. And then you also activate a kappa receptor, which is present in the pain relief circuitry, not present in the reward circuitry, but it is also present in some areas that cause dysphoria and some unwanted effects. But if you can activate only the interaction of those two receptors, and only when they come together, you can target certain tissues that have only that express both of those receptors.
Yeah,
right?
It makes sense. So instead of the drug coming in and sort of hitting every possible receptor that it touches, you've now created a drug that, in effect, it's only hitting quite a small subset, I would imagine, of all of the individual opioid receptors.
Right. And in this case, it's hitting the mu kappa interaction that occurs predominantly in the spinal cord circuitry that is responsible for pain relief. And so, So
the hope here, and I imagine this is what they're testing, is you can preserve much or all of the pain management side of things that you get with opioids, while at least lowering the addictive potential or the overdose potential.
Exactly. Right. And they work quite well, right? So Blue Therapeutics has a compound called Blue 181 that is similar in potency to fentanyl, but it does not have respiratory depression. It does not have tolerance. There's no place preference in rodents. And it really, it looks by all the preclinical measures like sort of the holy grail of pain relief, right? In that it has this profile where extremely potent, really strong pain relief, no tolerance, no withdrawal. And it's like I said, it's currently being developed, and I was full disclosure a part of that company until about a year ago when I stepped away to pursue these additional technologies in the space with Blackbox Bio, where we're developing these assays for screening of additional pain drugs, as well as psychedelics and some other compounds.
Interesting. So it sounds like where we're at in the pain world is there's actually people have developed drugs today that preclinically, meaning in rodents, are as potent or comparably potent to something like fentanyl. They work for pain as measured in rodents. They don't have the respiratory depression side effect, and they don't appear to be addictive or nearly as addictive. And so I guess I suppose it's just a matter of time before we know whether that holds for humans.
Yeah, I think so. It's there's a lot going on behind the scenes that I can't get into on a public podcast, but yeah, it looks really promising, and and I do hope that we do get to see these drugs tested in human trials.
So you mentioned that you are continuing work with this machine vision technology for doing automated behavior detection that we looked at previously, and you're doing things related to the psychedelic space, which I know you're really interested in. So what can you tell us about that stuff?
Yeah. So Blackbox Bio is the name of the company that is developing this mouse touchpad technology that I showed the videos of earlier. And what really came about there is that we realized pretty quickly that while this is super helpful in the pain space, and we want to develop a product, and we actually have a product. This is sort of my full-time gig right now, and we're selling these to different labs and drug development companies. We realized that it's not limited to just the pain space, but we can sort of automate detection of a lot of different behaviors that are important for a lot of different types of therapeutic areas, right? And I've long had an interest in psychedelics. And really, you've interviewed a lot of people on your show, and I'm sure a lot of the listeners are very familiar with the promise in the psychedelic space. And they've shown a lot of promise in for treating addiction and PTSD and anxiety, depression. And all of these disorders have common circuitry and similarities at a lot of different levels with chronic pain, right? So a lot of people with chronic pain have a traumatic trigger. They have, different, fear-based and emotionally, they have different emotional triggers that can cause the chronic pain, similar to how, people with PTSD can have emotional or situational triggers that can cause panic attacks and all these sorts of things. And so the thought here is that we can use some of these same tools that we can use to detect pain readouts in rodents, that we can use some of these same tools to differentiate between some of the different phenotypes behaviorally and experientially of broadly speaking psychedelics. And I'm using that term loosely to include entheogens and dissociatives, which I think we can likely differentiate using this black box detection technology.
I see. So one potential application here is, so again, this comes back to the problem of, we like to, in general, in research, people like to do work in animal models first and then pursue promising avenues that come from that in humans. So just like you can't ask a mouse if it's in pain and you have to come up with clever ways to assess the pain, you also can't ask a mouse if it's tripping on acid. You have to come up with some other way of doing that. Do you want to mention how that works today and how you might tie into that?
Yeah. So, right now, there's the psychedelic space is an interesting space because there's been a lot of anecdotal and really well-developed experiential literature on how people have experienced and used plant-based psychedelics, not just in modern times, but for quite a long time. And there are benefits and I'm certain a lot of uses for the naturally occurring psychedelics, but I think there are also a lot of potential use cases that could be developed using synthetics that are derived from these same compounds, and we can fine tune them to different indications and use cases and maybe find ways to fit them better into our current healthcare system. The difficulty there is that, or I should say a difficulty is that when you develop any new drug that's a new molecule that does not exist in nature, before you can test it in humans, you do have to test it in animals, both for efficacy and safety. Safety is something else that we're doing with the black box technology, but on the efficacy side, psychedelics, there's really just one readout behaviorally that is used to detect sort of the hallucinatory type properties of a psychedelic, and that is the head twitch in mice. And this is a rapid rotational movement that mice exhibit from all of the classical psychedelics, but it's a very infrequent behavior and it's very difficult to detect. And so you end up having to literally have people watching videos of mice for hours on end and writing down, a handful of head twitches that happen here and there. And the problem with this is that while it is quite sensitive to psychedelics, it's infrequent enough that it means that a lot of animals have to be used. It's expensive to do, and it takes a lot of time. So the first thing that we can do with the black box technology is that we can automate this, right? So instead of people having to watch this, we can automate it and just right out of the gate, detect these head twitches automatically. But beyond that, I'm convinced that we're going to see quite a few behavioral differences using some unsupervised machine learning approaches, where we will be able to differentiate not only between is this a psychedelic or creating hallucination-like effects or not, but even to sort of to really tease out, is this a compound that has entheogenic or empathogenic type properties? Is it anxiolytic, right? So a few of your previous guests have talked about, the psychedelics tend to act on the serotonin H2A receptor, which produces hallucinations, but also potentially a lot of the therapeutic beneficial aspects of psychedelics. But you also have the HT2B receptor. And so the HT2A, in addition to these, causes fear, right? Which is why, if you take a really high dose of LSD, people report, that they can have some really fearful experiences. Whereas the HT2B receptor, which is activated by compounds like MDMA, 6-APB, some other compounds, can actually be anxiolytic. And so we've got some readouts. I'm happy to actually show you a little video clip of how we can read out in real time using different measures that I showed you earlier, the present state of anxiety in a rodent using the same technology. So if you want, I'll show you another little video this of this. So let me go to this next slide. So anxiety in rats. So if you look at on the left here, we've got a rat. This is the same rat. So for those of you listening, there's a video of a rat walking around in a chamber, and his paws are illuminated using this touchpad technology, the Blackbox technology. And if you look at the contact points of the rat, it looks like he's standing on the pads of his feet. Mm-hmm. Instead of sort of the outline of a footprint, you see these points of light that are, sort of round points of light, like at the balls of his feet, right? And so that's what all the rats and mice for you're showing this so that we show that it works in both rats and mice, but see the same thing in mice. And that's what all the rats look like after they've just been handled. But if you leave the rat in the room and you leave the room, you see an entirely different footprint. So this is the same rat 10 minutes later. So I've left the room, just left the rat to hang out there, and they get flat-footed. And if you think about it sort of intuitively, it makes sense. It's almost like I think it's a vigilance readout, right? Mm-hmm. So, if a rat is scared and sort of wanting to be ready to run, they're kind of up on their tiptoes, just like a human sprinter would get on their toes to start a race, right? Mm-hmm. And when they're calmed down, they get flat-footed. And so we have this anxiety-related footprint, and that's dramatically different from the calm or the anxiolytic footprint. And we see this. It's not just after human handling. You can even if you go to the door of the room where these animals are housed and you just jiggle the doorbell, it'll immediately go from this flat-footed appearance to on the tiptoes again.
This makes a lot of sense. And I guess, the idea here overall is, using these objective readouts, you can not only do behavioral assessments faster and more cheaply, you can actually just detect things that you wouldn't have been able to detect before. And this isn't limited to pain. It's in theory, anything. Right.
No, exactly. And just to mention a similar thing that, because I, really have this interest in the psychedelic space. So this is actually a video of, it's actually a cropped video that I showed earlier. And this is just showing a flinch and lick response. So I'll play it again. So if you watch what this mouse does, so let me see here. I got to think. It's his left hind paw is injured. He has an inflammation model. So his left hind paw, which is a little less bright, is presumably in pain, and he kind of flinches it and then licks it. Mm-hmm. Right. And so I'll stop the video here right at the point. So right here, he flinches, he shakes it, and then right after he shakes it, he licks it. And this is a very common sequence, right? And so if you apply a heat stimulus to the foot of a mouse, they do the same thing. They flinch it and then they lick it. But with dissociative drugs like ketamine and other compounds, they will flinch,
but not lick.
You see that they have this pain phenotype, behavioral phenotype, but they don't lick it. They don't attend to it, right? It's like they're aware that it hurts, but it's not bothersome, maybe. I mean, anthropomorphizing here, but point being that this is another behavior that we can automate, right? Mm-hmm. So, and you can imagine when you start stacking these behaviors on top of one another, it makes it quite easy to to tell for a novel compound, is this, if you're a drug, psychedelics development company, which is a lot of activity in this space, and you've got 20 new compounds, and you think they're likely from some of the cell-based assays and other approaches to be have psychedelic-like properties, but is it more like MDMA? Is it more like an LSD or psilocybin, or is it even potentially a dissociative compound, right? And so we can behaviorally really distinguish between all of those, and that's sort of the next thing that we're doing there at Blackbox commercially, is that we are in the process right now of setting up a contract research organization in the Dallas-Fort Worth area to do high throughput screenings for third parties. So we're not doing any of our own drug development work. We're simply setting this up as an assay to provide service to the psychedelics drug development space for anyone that's developing compounds and really wanting to tease out, what kind of compounds do they have prior to entering into humans.
I see. So it sounds to me like there's two things going on that will synergize in terms of what you're doing with this.
Right.
One, you could just have someone, let's just say you had a research lab, whether it was academic or private, you were interested in screening compounds to see if they might be hallucinogenic. Today, the way that people do that is they have a researcher spend probably hours and hours looking for this head twitch response in video. Right. So you guys can just automatically detect that so that they can do that type of screening faster.
Right.
The second thing that it sounds like you're doing is you could, if you gave different groups of animals different drugs, by videotaping them and using machine visions in the way that you've shown us, you could create a kind of behavioral fingerprint for each drug. Right. In other words, animals, when they get MDMA, they tend to do these types of behaviors, but not these ones. Those that get LSD, there might be some overlap, but it's different. Even something like psilocybin versus LSD might have small differences between them. And then you could take a completely novel drug, say, and just compare it to all of those known drugs with known effects in rodents and known subjective effects in humans. And in theory, that should be able to give you quite a bit of predictive power for what a novel drug will actually feel like.
Yeah, we hope so. And I think that will be the case. And I'm excited to figure it out. I mean, that's also one of the beauties of science, right? Is that you come in with these hypotheses and some data suggesting that it should work a certain way. And then you give it a go and see how it does. So,
Interesting. Last area I want to ask you about, David, is, since your expertise is in pain, and that's what we mostly talked about, is there any indication you have or anything you might speculate on in terms of whether or not any of the psychedelics or dissociatives or other drugs like that have any potential related to pain? That, the one thing that comes to mind here for me, to get you thinking on this is, I know a lot of these drugs actually have sometimes very potent anti-inflammatory effects that might be so potent that you could use sub-psychedelic doses to achieve them. So what are your thoughts in that direction?
Boy, that we could do a whole nother podcast on this topic, but I think that there's a lot of promise, there is a lot of promise, and I think that it's interesting, the psychedelics, because they have been scheduled as, and for those not from the U.S. or not familiar with the FDA/DEA process for controlling substances in the U.S. It's similar in other countries, but the psychedelics have basically been put really arbitrarily into a category of saying they have no clinical benefit, without, despite the evidence that's been around for decades showing that they do have clinical benefit. But the downstream impact of this has been that it's been virtually impossible for academic groups in particular to study these compounds at length and to look at, what are the anti-inflammatory properties of these compounds, and can we harness that to develop a therapeutic? So certainly, all the way from the various psilocybin strains of mushrooms to peyote and other compounds, there are a wide range of anti-inflammatory compounds and molecules, right? Terpenes, triterpenoids that are present in these compounds. I'm particularly interested in the cacti and some of the mescaline related compounds, as well as triterpenoids that are in the cacti and how they may have analgesic properties. And but also I think that there's really a lot of interesting overlap and potential synergy between the ways that psychedelics are being used with psychedelic-assisted psychotherapy for anxiety, depression, and whatnot, that could translate to using the same approaches for treating chronic pain. Mm-hmm. So we know that a lot of chronic pain is kept alive. I shouldn't say we know. There's a lot of evidence to support the hypothesis that in many cases chronic pain is kept alive and kept chronic by a fear of the pain itself, right? And I've experienced this, right, where you have a bruise on your leg, right, from kickboxing, and you're not thinking about it, but you almost run into something, or you have something that triggers a fear of that pain, and as soon as you have that fear, suddenly you're aware of the pain again, right? Mm-hmm. And so for people that have traumatic experiences that are tied to their chronic pain. My folks, I mentioned earlier in the podcast that they were in a plane crash, and my mom still today has a lot of chronic pain, and it's like clockwork when she has sort of some emotionally challenging experience, or when things related to her plane crash come up, her chronic pain is back, and it's debilitating. It can even put her in the hospital, right? Mm-hmm. And so having seen this firsthand, with her, and also just kind of understanding, how central sensitization works, it makes sense to me that the psychedelics do hold a lot of promise for chronic pain, and it's a space that I hope to move into in the future.
Yeah, I mean, what you're saying is evocative of more or less what seems to be going on with something like MDMA for PTSD, at least conceptually. Right. It's sort of somehow dampening the strength of the association that someone has with some past traumatic event. And right. That's more or less, I think, what you're referring to here.
Yes, no, exactly. And it's really an exciting time. And I think there's a lot to be hopeful for chronic pain patients. And, a lot of activity, investment, development is needed, as well as a lot of advocacy, I think, for both for continued funding for developing these therapies, as well as continued access for the plant-based compounds that people would like access to prior to the release of these marketed FDA-approved compounds.
Mm-hmm. Well, I think that's a pretty good spot to end it, David. Thank you for your time and for all you've shared with us. And I look forward to following what is on the horizon for some of the stuff that you're working on.
Thank you, Nick. And I really appreciate your time as well.